So, we will continue with the properties of the Lebesgue measure. We saw some of them in the last few lectures. So, we ended up with proving this result that if you have a linear transformation T from R k to R k, then the measure of T e, where E is a Lebesgue set, is some constant times the Lebesgue measure of E itself. The constant depends only on the linear transformation T, that is what we proved. Today we will start with the result that the constant which comes out is actually the determinant of the linear transformation. Okay. So, I will also clarify why T of E is measurable whenever E is measurable. So, we will start with that assertion which I should have clarified in the last lecture, and then we will go on to prove that the measure of T e is actually determinant of the linear transformation T times measure of E. Okay. So, let us start. So, we have a linear transformation T from R k to R k. Okay. So, this is a linear transformation and what we have proved is if E is a Lebesgue set. So, before that let me clarify that we constructed the Lebesgue measure and we got a sigma algebra and the measure, right. So, this is same as the triple we already had. Okay. So, this is R k and we have the Lebesgue sigma algebra R k and the Lebesgue measure M. Okay. So, in one case we constructed using the outer measure, in the other case we constructed using the Riesz representation theorem, but both of them give us the same sigma algebra and same measure. Okay. So, if E is a Lebesgue set, then T of E is also a Lebesgue set and the Lebesgue measure of T of E is actually equal to some constant which depends only on T times the Lebesgue measure of E. Okay. So, we had two cases, one was T is singular. If T is not invertible, then range of T. So, this is the easy part, range of T is a subspace of subspace of R k and has measure 0, and so measure of range of T is 0. Subspace is closed, so it is a measurable set. So, range of T, this is a Borel set in fact. Okay. So, there is no problem in looking at measure of that set. And so, if I take any E, so for every E in the Lebesgue sigma algebra of R k, T of E of course sits inside range of T, but range of T has measure 0. So, this is a measure 0 set, and so this is a subset of measure 0 set, and so will belong to Lebesgue sigma algebra for R k. So, it makes sense to look at M of T e, and this is of course 0, which is delta T times M of E, where delta T is 0, right. So, this is the determinant of T, T is singular. So, its determinant is actually 0. So, we will prove that delta T is actually the determinant. But before that let us look at the remaining case. So, B, T is invertible, right. If T is not singular, then T is invertible. Well, what does that mean? So, that would mean that T is a linear map from R k to R k, which is 1 1 on 2. Okay. And so, T, well, any linear map is continuous, and so inverse also is continuous because it is 1 1 on 2 linear, right. So, T inverse is also continuous. In other words, T is a homeomorphism, of R k. Okay, so it's a very nice map. Okay. So, first let us justify why, if E is a Lebesgue set, if E is a Lebesgue set, let us justify why T E is also a Lebesgue set. Okay, so, this follows from various properties of T. So, T is a homeomorphism. Okay. So, let us give a simple exercise here to use that. Suppose I have a homeomorphism from R k to R k. Okay. What does that mean? I have its 1 1 on 2, f is continuous and f inverse is also continuous. Okay. Then f of E is a Borel set if and only if E is a Borel set. Okay, so, consider this as an exercise. So, the hint does use, it is not difficult, hint does use good sets principle, and use good sets principles along with the properties of the homeomorphism. F of an open set is open because it is a homeomorphism, and f inverse of an open set is open. So, it takes open sets to open sets, and so it will take Borel sets to Borel sets. So, use that. Now, I know that E is a Lebesgue set and I want to prove T E is also a Lebesgue set. E is a Lebesgue set tells me, because R k, so this is a consequence of the Riesz representation theorem. R k has the property that every open set in R k is sigma compact. So, that tells me, as a consequence of the Riesz representation theorem, there exists sets A which is f sigma and B which is G delta such that A is contained in E, contained in B, and that is the important part, B minus A has measure 0. Okay. So, this is a property of the Lebesgue sets which we already know, and it was also proved using the Riesz representation theorem. Okay. So, because of this, so now if you look at, I am looking at T E, right. So, apply T to this. So, I will get T of A is contained in T of E, contained in T of B. This is trivial of course, but T of A, what is T of A? A is f sigma. So, T of A is also f sigma and this is G delta, right. F sigma, remember, is the union of closed sets, G delta is intersection of open sets, and T is linear and 1 1 on 2 and all that. So, all the set theoretic operations will be respected, and T will take open sets to open sets and closed sets to closed sets. So, that is all is used there. Okay. So, use the fact that T and T inverse map open sets respectively closed sets to open sets and respectively closed sets, okay, and the fact that T is 1 1 and on 2. Okay. So, everything, all set theoretic operations will be respected essentially. So, T E is sandwiched between an f sigma and G delta, which is what we want, but we want a little bit more. So, we look at the measure of T B, which is a G delta set, minus T A, which is a f sigma set. Well, what is this? This is m of T of B minus A. So, this is something I will leave it to you to check. It is a set theoretic equality. T B minus T is linear, T B minus T A is T of B minus A. this is equal to delta t times m of b minus a, this we already know. Okay. So, yeah, maybe I should explain this. Okay. Well, okay. So, maybe instead of this I will leave this as an exercise to you. If E is a Borel set and measure of E is 0, then measure of T E is also 0. So, T has the property that it takes sets of measure 0 to sets of measure 0. Okay. So, this is another exercise. It is true for much more general functions which are Lipschitz, but for the time being linear T will do for us. So, this will give us 0. Okay. So, I have a G delta set, I have an F sigma set such that difference has measure 0 and T E is sandwiched between them. So, this tells me that T E is measurable. So, T E is a Lebesgue set. So, it makes sense to talk about M of T E. Okay. So, I wanted to justify this. So, that is what we did, and from yesterday's proof we know that M of T E will be delta T times. So, we have a constant. So, if let me write this as a statement, if T from R k to R k is linear, then there exists a constant delta T such that M of T E is equal to delta T, that is a constant, times M of E, okay, for every E Lebesgue set. Our aim is to compute delta T. So, claim the constant delta T is actually equal to determinant of T. Okay. So, T is a linear transformation. So, you can choose a basis, write down the matrix of T and then calculate the determinant, that would be your delta T. Well, modulus of determinant of T, because it is a positive quantity. Okay. So, let us prove this. So, again the singular part is trivial, T is singular, that is the first case. Then delta T we know is 0, which is equal to the modulus of the determinant of T, right. T is singular. So, the determinant T is not invertible. So, determinant of T is 0. So, we need to look at only the case where T is invertible. Okay. So, before we go further, notice that. So, note that if I have, if T 1 and T 2 are linear on R k, then M of T 1 acting on T 2 E. Okay. So, T 1 composed with T 2 is another linear map, right. So, this is equal to, because of the way delta is defined, delta of T 1 times M of T 2 E. Okay. But M of T 2 E is delta T 2 into M of E. So, delta T 2 times measure of E, that is the right hand side. Left hand side I can write as measure of the linear transformation T 1 T 2 acting on E, right. T 1 times T 2 is the composition of T 1 and T 2, and that is another linear transformation, which I know is the delta of T 1 T 2. So, now my linear transformation is T 1 T 2, right. So, I have this. So, these two are equal, which means delta T 1 T 2 is delta T 1 into delta T 2. So, that property is there. So, delta T 1 T 2 is equal to delta T 1 into delta T 2. Okay. So, let us prove the claim, right. So, claim is that delta T is, so we are assuming T is invertible, and claim is that delta T is the modulus of determinant of T. Okay. So, we will use some results from linear algebra. I will not prove that. Let E1, E2 etcetera Ek be the standard basis for Rk, right. So, Ej is simply 0 0 0 1 at the jth place and 0 0 0, right. So, this is the jth place. Okay. So, we use the following fact. So, I will write it as a fact. Every linear transformation on R k is the product of finitely many linear transformations of the following type. So, what I am saying is any linear map is the product of the following type. So, I will write down 3 types. 1, T E1. So, we have fixed the basis E1, E2, Ek, which is the standard basis. T E1, T E2 etcetera T Ek is a permutation of E1, E2 etcetera Ek. Okay. So, such a T is of course invertible and so on, and you will have the matrix of T would be a permutation matrix, right. So, the determinant of T is plus or minus 1. In this case, determinant of T is plus or minus 1. Okay. So, modulus is 1. Second case, okay, T E1 equal to alpha times E1, where alpha is some constant and the other ones are fixed. So, T Ej equal to Ej for j equal to 2, 3 etcetera up to k. So, then the matrix of T, with respect to the standard basis, E1, E2, Ek will take the form. So, E1 goes to alpha I1. So, I will have alpha here 0 0 0 and well everything else is fixed 0 0 0. So, I have 1 here and so on, right. So, the determinant of T is equal to alpha. The third one is the slightly complicated one. T E1 equal to E1 plus E2 and the other ones are fixed. So, T Ej equal to Ej for j equal to 2, 3 etcetera k. So, how will the matrix of T look like? Well, E1 goes to E1 plus E2. So, I will have 1 here and zeros, then I have ones on the diagonals, right. So, this is how it would look like, and the determinant is of course 1, determinant of T is equal to 1. Okay. So, this is a fact we will be using, that every linear transformation on Rk is the product of finitely many linear transformations of the following type. And since we know that delta is So, let us write one more line here. Since delta of T1 T2 or any product if you like is delta T1 into delta T2 and the same for determinants, right. Determinant of product of two matrices is the product of the determinants, determinant T1 and determinant T2. If we have inequality at these types 1, 2, 3 where delta T is equal to determinant, then because every linear transformation is a product of these three things, we will, and using these two facts we can extend it to all linear transformations. So, it is enough to prove. So, enough to prove that delta T is equal to modulus of determinant T for T of type 1, 2 or 3 because of the product property. Okay. So, let us start with that. So, in the first case what is T? So, let us go back. T is the T is a permutation of E1, E2, Ek. So, if I fix the cube unit cube Q, so unit cube Q, then T of Q is equal to Q, okay, right, because it is the. So, in dimension 2 I am looking at this cube. So, 0 0 1 0 1 1 and 0 1. So, all that you can do is permute E1 and E2, this is E1 and E2. So, if you permute them you will still, the cube will be fixed. So, m of T of Q is equal to m of Q, right. To calculate delta T it is enough to calculate the measure of one such set, right, but this we know is delta T times m of Q, which implies delta T is equal to 1, which is the modulus of the determinant, right, because in the first case determinant is 1 plus or minus 1. So, modulus of, right, plus or minus 1. So, modulus of that would be 1. Okay. So, this is equal to modulus of determinant of T. So, first case is done. Okay. Okay, that was easy. Second case, well, in second case what happens to the unit cube? So, let us look at that. Second case T E1 becomes alpha E1, everything else is fixed. Okay. So, if I take Q to be the unit cube, T of Q, what would be that? So, let us see. So, this is the unit cube. So, let us draw this. I have 1 0 here, 0 1 0 0 here, 0 1 here and 1 1 here. So, this is my cube. Now, I apply T. Well, T multiplies E1 by alpha. So, this will go to alpha 0, right. So, this goes to alpha 0 wherever that is, the remaining things are fixed. So, this goes to 0 1 and then you add up, right. So, you will have something like this. Okay. So, this is alpha 1. So, all that has happened is this side becomes alpha, right, and this side stays 1. So, that happens in all dimensions except one side, everything else becomes alpha. So, T of Q, if I look at measure of T of Q, well, measure of T of Q, what happens? I have one side alpha, then I have sides 1. So, I multiply all of them, right. So, I will get alpha into 1, which is measure of Q, right. But this we know is delta T times measure of Q, which is 1. So, delta T has to be equal to alpha, which is the modulus of the determinant. So, delta T is equal to alpha equal to modulus of the determinant. Okay. So, let us do the third case. Third case is the one which is slightly complicated. So, remember the third case T E1 is E1 plus E2 and other things are fixed, T Ej equal to Ej for j equal to 2, 3 etcetera up to k. So, let us write down what is T of q, I will write down and then explain. So, T of q is equal to all those points of this form psi I E I equal to 1 to k, where psi 1 is less than or equal to psi 2 less than psi 1 plus 1 and the remainings are all fine. So, psi I less than 1 for I not equal to 2. Okay. So, we will do this in R2 and see how the picture looks like. So, I have 0, 0 0, 1 0 which is E1 and 0 1 which is E2 and 1 1 which is E1 plus E2, right. So, I have this cube, I apply T to it, right. So, I am going to get the image of this cube, let us see where it goes. So, E1 goes to E1 plus E2. So, E1 plus E2 is this vector, right, 1 1, okay. E2 goes to E2. So, that is again this vector. So, that is 0 1, okay. So, I know this vector. So, let us use some other color, this vector goes to this vector and this vector goes to this vector, right, all right. So, the anything here is the sum of these two vectors. So, it will go to the corresponding sum. So, you complete the parallelogram, you will get exactly what is the image of q under T. So, this would be your T q. Okay. So, some more steps to complete this. So, keep the picture in mind. So, let S1 be contained in T of q, be the set containing points in T q with psi 2 less than 1. So, second coordinate has less than 1 and S2 the rest, S2 the rest. So, let me denote it here, psi 2 the second coordinate is less than 1, right. So, what do you do? So, you look at this line and whatever is here, right. So, this would be your S2 and this is S1, okay. And of course, there are other coordinates in the higher dimensions. So, which I will not draw. So, if I look at measure of TQ, this is equal to measure of S1 union S2. So, that is a disjoint union, right, which is equal to measure of. So, this is measure of S1 plus measure of S2, which is equal to measure of S1 plus measure of S2 minus E2. So, this is the usual subtraction here. I am translating the set E2 by S2 by E2. So, what do I mean by that? So, let us see. Well, maybe I change the notation properly. I should be subtracting the other way. So, maybe S2 here and S1 here. So, the S1 part, if I subtract by E2, this portion will just come down here and I will get this triangle, right. This would be my triangle S1 minus E2. But then these are still disjoint and so I have M of S2 union S1 minus E2, okay, which gives me the original cube Q, which is 1. So, M of T Q, I started with M of T Q, I ended it with M of Q. So, delta T is equal to 1. delta t is actually equal to 1, which is the modulus of the determinant of t. Okay. So, we stop here for the time being. We just showed that if T is a linear transformation, it maps Lebesgue sets to Lebesgue sets, and the measure of T of E, where E is a Lebesgue set, is modulus of the determinant of T times measure of E. We will see that these properties of the Lebesgue measure, which is translation invariance or the behavior with respect to the linear transformations etc., actually gives you some change of variable formula. So, in the next lecture we will start with that, and then we will go on to look at other sets with some special properties. Okay.